In this video, I'm going to be talking about Newton's first law, what it is, and how does it apply in these situations. Newton's first law is that an object will remain in its state of motion unless acted on by an unbalanced force, which is also known as the law of inertia. So before getting further into Newton's first law, let's talk about what inertia is. Inertia is the tendency of an object to remain in its state of motion. So it's basically a property of all matter that describes how likely it is to keep on doing what it's doing. And because inertia doesn't specifically have a unit of its own, it is measured by the amount of mass that an object has. So when you see how much mass an object is composed of, that number in itself will tell you the tendency of an object to remain in its state of motion, and it is a direct relationship. So now going over here and getting into the details of Newton's first law, it's basically saying something is going to stay at rest or be moving at a constant velocity, which means going exactly the same speed in the same direction, unless an external force or forces pushes or pulls and then creates an imbalance and then causes that object to accelerate. So to put it in simple terms, it's basically saying something is going to keep on doing what it's doing unless it gets pushed or pulled and then an imbalance causes it to accelerate. For example, if there's a rock floating along in space going at 10 meters per second, it's going to be going exactly 10 meters per second in a perfectly straight line unless it's affected by an outside force that causes it to accelerate. A lot of Newton's first law applications typically apply when there is something in some sort of container. So what I mean by that is a person in a car or even a brain inside of a human skull. So let's take a look at this car on the left side over here. So say for example, the person and the car system are moving forward at 30 miles per hour. And then it decides to take a right turn. So if you picture yourself sitting in a vehicle and it takes a sharp right turn, what happens? It feels like you're being pushed to the left. Well, you're not really being pushed to the left. It's just the entire car is moved to the right and gives you the feeling like your body is being pushed to the left and that your left shoulder might kind of lean against the door. But what you're actually doing, just like the car, is you're moving in a straight line at 30 miles per hour. Now, because you're not rigidly connected inside the car, when it turns, you continue in your state of motion, which is a constant velocity of 30 miles per hour in a straight line. So as you continue forward in a straight line, you see where the tip of that arrow ends up? It ends up on the left side of the car. And that's why you have that sensation of feeling pushed towards the left to the left side of the car. But really, it's just you and your inertia keeping you in the same direction at 30 miles per hour as the car is turning to the right until you eventually kind of catch up with it and then continue in its state of motion. Another example is this example on the right, which is actually a very similar example, although it may not seem like it. It's when someone gets a concussion. So say, for example, someone receives a lot of force on the front part of their skull. Now, because the brain isn't rigidly connected inside the skull, it's basically sitting there with a watery membrane around it. So if you get struck with a lot of force in the front of your skull, it's going to cause your skull to move and accelerate really, really quickly to the left. And what is everything doing initially? It is at rest. Okay, so because the brain is at rest, it has a tendency to stay at rest. So the brain is actually going to collide with the front of the skull because the skull moves to the left. And as the brain remains at rest, the front of the skull is basically bumping into the front of the brain. And what typically happens in a concussion is that the skull moves without the brain, it collides with the brain, and then that's where the first collision happens, and then the brain actually typically moves back and gets a little bit of trauma on the backside of it as well. Okay, so that's a case where The object, which is the brain, is trying to remain at rest and it has inertia. And then there's a lot of acceleration with the outer part, which is the skull. So as it moves to the left really, really quickly, it contacts the front of the brain, causing the first part of the concussion. So basically, what Newton's law is a lot of different applications and examples where something is continuing in its state of motion, which could either be going at a constant velocity or being motionless, unless there's some kind of force that affects it. So in this first case over here, there might not be a force that affects it, so it moves at 10 meters per second in a straight line. And then in the case of the car and the concussion, the brain and the person remain in their state of motion as long as they can until their container being the car or the skull, affects it and causes it to accelerate. Newton's second law, what is it and how is it used? Newton's second law is basically F net equals mass times acceleration and all the relationships involved within that formula, which are the net force is directly proportional to the acceleration, and then also the mass is inversely proportional to the acceleration. So to fully understand the formula, you want to make sure you definitely know what net force is. It means the total force that's acting on an object. So although there might be multiple things pushing or pulling on it, the net force is the final number representing how much unbalanced force is pushing or pulling on it. For example, if you have a box over here with 5 newtons pulling to the right, and you maybe have 2 newtons of force opposing that 5 newtons, then you would say that your net force is 3 newtons to the right. All right, so let's go ahead and take a look at some of those relationships that were mentioned in this box over here. So the first one is we have 2 of these scenarios here where the force being applied to the right is 100 newtons for both of them. So the force is staying constant, but the mass of our box is changing from 10 grams to 20 grams. So we have 2 times the mass. Now, earlier we said that mass is inversely proportional to acceleration. So that means that if the mass goes up, the acceleration must go down. And it is an inverse relationship, which means that if you have 2 times the mass, if you take the inverse of 2, that is 1/2, you have exactly 1/2 the acceleration. In the other relationship that's shown below right here is that force is directly proportional to the acceleration, the first one we mentioned over here. So in this case, we have a constant mass of 20 kilograms for both of our objects, but we have a force of 10 newtons that is cranked up to a force of 30 newtons, which means that if we have 3 times the force, that means that as the force goes up, the acceleration also rises directly. And if we have 3 times the force, then we also have 3 times the acceleration. Now, my last example is more of like a real world example. So we have 2 different football players here. Looks like we have maybe a wide receiver and a lineman in all kinds of different sports. You're going to notice that depending on the type of sport or the type of position being played in a sport, the athlete has a particular build. If it's someone who has to accelerate very frequently, they have to speed up, they have to slow down, they have to change direction, they're going to tend to keep their mass down so that they're able to increase their acceleration a little bit more easily. So all these athletes are going to build up their muscles so they are able to apply lots of force. In some cases, some of these athletes even apply 5 times their body weight of force into the ground to make themselves accelerate very, very quickly. And in this case over here, where a lineman does have to accelerate, it might be more important for him to have more mass. And these linemen who have more mass tend to not accelerate quite as much. Okay, they do need some acceleration, but they don't need quite the amount of acceleration as someone like a wide receiver that may need to speed up, slow down, and change direction very frequently. So there's a lot of different applications that you could use this with. You can use it with cars, you can use it with athletes, you can use it in simple situations, as we stated before. But Newton's first law, or excuse me, second law, is basically the application of this formula: net force equals mass times acceleration, and using both of these relationships within it to solve for different scenarios. Newton's third law, what it is and how it applies to a bunch of different scenarios: it's that every force has an equal and opposite force, and that all forces come in pairs. It's oftentimes said that Newton's third law is every action has an equal and opposite reaction. And I don't particularly like that definition because it sounds like the force is being applied and then another force is reacting to it and pushing or pulling shortly after, when in fact the force pairs are happening simultaneously. So let's get into our first example over here, where a truck is crashing into the car. And as the truck is crashing into the car, it applies a large force onto the car towards the left. And then at that same moment, the car is pushing back on the truck to the right. And these forces are equal in magnitude and their amount of force, and opposite in their direction. Now, if you take a look at these two vehicles after the crash, you might be thinking, didn't the car get more damage because there's a really large dent in the side? And didn't the truck get less damage because there's only a little scratch on the front? Well, the results can make the amount of force seem to be different, although they are not. And the reason why the results are significantly different is because you're talking about two objects that are significantly different in their mass and their construction. So you can't compare the results of what happens to both of them and then say one gets more or less force, when in fact every force always has an equal and opposite force. Going to our second example over here, basically the reason how anything moves is it's depending on something else. So as you push or pull and you get that equal and opposite force, that's the thing that's actually propelling you forward. For example, when you're walking or running forward, your feet are pushing back, and that equal and opposite force that you get from the ground is the one that actually propels you forward. Same thing with swimming. As you push the water back, the water pushes you forward. Okay. In this case over here, this is a classic case of Newton's third law, where a space shuttle is taking off into space, and it would seem like it's actually pushing off of the ground, which it's actually not. What's happening is that these rockets are ejecting a large amount of gas downwards, and as the rocket pushes a lot of gas downwards, the gas pushes the entire space shuttle upwards. Now you might be wondering, how can you push out gas and lift an entire space shuttle and these rockets up into space? Well, the reason being is because there's lots of propellant, lots of gas being shot downwards, to the point where there's maybe 20,000 pounds of propellant being released per second in order to push this space shuttle upwards. So in a lot of these cases, what you can do is you basically write out what's happening with one of the forces and you switch the nouns and the direction. So let me show you an example before I explain in more detail. So if you're analyzing any force, like I was saying, you can switch the nouns and the direction. So what I mean by that is the initial force that you might be paying attention to is how the rocket pushes the gas down. Now, if you switch these two nouns, the rocket and the gas, and then the direction of it, then it's the gas pushes the rocket up. That's the equal and opposite force. So in all these cases, you can apply that same sort of strategy where the hand pushes the water back and the water pushes the hand forward. And then the foot pushes the ground backwards, and then the ground pushes the person forwards, and then so on. The last scenario that I want to bring up is a person doing an ollie on a skateboard, and ollie is basically just doing a jump on a skateboard. Now, if you jump straight up on a skateboard, you're not really going to make the skateboard rise off of the ground. Your feet are just going to rise up away from the skateboard. So what's actually happening is an example of Newton's third law. What you would do is you would apply force on the back part of the skateboard, and as you apply force on the back part of the skateboard, it pushes down into the ground, and then the ground is going to have a normal force that is equal in the opposite direction, and that normal force pushes on the board and then makes the board rise up off the ground. So basically what it is, it's a controlled collision between the skateboard and the ground that allows the skateboard to rise up off the ground, and then in addition, the friction between the person's feet and the skateboard could help pull the skateboard up a little bit more, and then you can jump off the ground in that case. So in all these different scenarios, like I said, every single force has an equal and opposite force, and all forces come in pairs. And if you use this strategy right here, like I said, what you can do is basically switch the order of the nouns and switch the direction, and that will be able to identify the other force that's present. Thank you for watching and listening.